All right, let's start. Hello, everyone. I'm Cyrus Shahabi from USC, sitting in Los Angeles. It's 11:30 a.m. my time. I think everybody coming from different time zones. I probably in Asia is late midnight or early morning. So thank you for participating. This is session 7, research session 7, mining time series and spatial data. I'm the session chair. Professor Werner Naht is the co-moderator helping me in case something goes wrong. And then, of course, Yonjin, as a student volunteer, he's running the show pretty much. So what we're going to do, we have 5 presentations. We're going to play each video, which is about 15 minutes, one after the other. In between, we have 3-4 minutes for questions. If the authors are around, I think we're missing 1 or 2 authors. What I would like you to do is please enter your questions into the chat or in the Slack. Either one is fine. We try to monitor the chat and the Slack and then select some questions to be asked in between the presentation. So with that, I think we can start with the first video. Maybe while we're doing this, is the first paper, Spatial Transition Learning on road networks with deep probabilistic model. And I think the presenter is Xichang Li from NTU. Yongzhou, are you trying to upload the video?
Give me 1 second.
Oh, okay, sorry.
Xiu Cheng from Nanyang Technological University. Today I'm going to present our work, Spatial Transition Learning on Road Networks with Deep Probabilistic Models. Here is the outline. First, I'm going to introduce the research problem and motivations, then summarize the contribution of this paper. Then talk.
So the video is working or not?
No, I can't see the video.
Okay.
Do you want me to try from my side?
Yes. So,
maybe a good idea.
Yeah. Try if you can.
Okay, let me see which one is the. This is 189, right?
Yeah, the first one.
Okay. Is this working fine?
Oh, there is no sound. So
exactly, sound is missing.
Yeah. So when you share the screen, you have to check the box on the left corner. So that they will play the sound from your computer.
Okay, let me try one more time. Share screen. Left corner.
So there's the mute sign for the microphone.
Yeah, that one was unmute because you could hear me, right?
Yes, I can hear you, yes.
So now I'm going to play the videos and then I'll mute myself. Maybe that works. That work?
No.
No.
Maybe we have to wait a few seconds when the speaker starts.
Okay.
Let me. Thing is that when I start sharing, I lose my control. Oh, there we go. Still not working?
No.
So the audio is not working.
So let me try one more time. I'm gonna stop your.
Okay.
Everyone, I'm Liu Cheng from Nanyang Technological University. Today I'm going to present our work, Spatial Transition Learning on Neural Networks with Deep Probabilistic Models. Here is the outline. First, I'm going to introduce the research.
This is working?
Yeah.
Yes,
Okay.
it's working.
Okay, okay.
Research problem and motivations, then summarize the contribution of this paper. Then talk about our proposed method, then give the experiment result. First, in this study, we explore the problem of given origin and destination. We try to predict the most likely route on the neural network, as well as assign a probability to any possible route between these origin and destination pairs. The first motivating example is that in text dispatching systems, the origin and destination are already known before the start of a trip. Thus, predicting the most likely route could help us picking up the potential passage that are waiting on or nearby the most likely travel route. The second motivating example is route recovery from sparse trajectories. Here, the figure showing that there are trajectories with sampling points A1 to A5. Due to low sampling rates, there are two possible routes between A3 and A4. So usually we know the travel time between these points. So the problem of inferring the most likely route can be formulated as this one. Inferring most likely route condition on T. Using base rules, we can decompose it into the product of the density of travel time T condition on the route and the spatial transition probability of the route R between the origin and destination. So our work is related to sparse trajectory similarity computation and route recovery from sparse trajectories, as well as future movement predictions. So, however, in this paper, we argue that three key factors in spatial transition model need to be considered. First is that the spatial transition pattern demonstrates quite strong sequential properties. So the figure showing the neural networks and the table showing the trajectories collected from these neural networks. Now consider that we try to predict a car driving on R2. Then, if we solely based on the current route, R2, we may conclude that the car is more likely to transit to R4, because R4 had a very high frequency, the first trajectories. Now, what happens if we know that this car also driving from R1? So we may change my mind that this car is more likely to transit to R5. Second is that the trip destination has a global impact on the transition. Now also consider these examples. Now a car is driving on R5, and its destination is C. First, without considering this destination, we may think that the car is more likely to drive to R6 because there are more instances of such patterns. But what happens if we know that each destination is C? Then we will be almost sure that the car will be driving to R10. The third is that route choice are also influenced by the real-time traffic, because the vehicle drivers tend to choose those less congested routes rather than those shortest one. So here is our contribution. We develop a deep probabilistic generative models, DeepST, to learn the spatial transition patterns, which concern all the three key factors. We also propose a novel adjoint generative models to learn the key destination proxies. It enables effectively sharing statistic strengths across trips, and also the model is robust to the inaccurate destination. To scale the model to large-scale dataset, we develop an efficient inference method within the variational autoencode frameworks. Here is our high-level idea of the proposed method, DeepST. So we attempt to generate the observed trips by conditioning on the 3 key explanatory factors as aforementioned sequential property and global impact of destination, as well as real-time traffic condition. Here is the generative process. We first join the real-time traffic indicator C. Then to generate a trips, we recursively perform this procedure. First, to join the next route links, we condition on the past travel route, destination X, and real-time traffic. Then we measure the distance between the new generated route links and the destination to decide whether to terminate this process. Here's the graphical model. So the key part here is that how to model these conditional probabilities. In this paper, we condition that this is an additive function between these 3 key factors. Here FR represents the past travel route, the reputation, and Fx is the reputation of destination X. Here alpha, beta, gamma are the projection matrix, which try to project from the latent space to the route link space. So first, how to model the past travel route. To capture the long-range dependency, we simply adopt the GRU IN. So we initialize it with 0 vectors and update R according to this equation. Then the output of the GRU will be the representation of the past travel route. Second is that how to represent the destination. The trip destination has a global impact on the transition behaviors, and also there are some previous proposals assume that the destination route links are available and learn the reputation to guide the route decision. However, the exact destination route link may not be available because the driver may not drop the passenger exactly on the street as he requested. Second is that learning reputation for each route link separately cannot effectively share the statistical strengths across trips with spatially close destination. So we again use the previous example to illustrate the second point. Now consider a cartography on R5. If we treat A, B, C destination separately, we may have an equal probability for R10 and R6. Now, know that A and B are spatially close, that if we use one representation AB for them, which will get that the car is more likely to transit to R6. Then to see, the transition patterns can be shared to mutually reinforce the transition probability between R5 and R6 across trips. So this inspires us that the trips whose destinations are spatially close should share similar destination representation. More importantly, the learned destination representation are able to effectively guide the spatial transition of the trips. To this end, we propose to learn key destination proxies shared by all trips and adaptively allocate the trips into one of these destinations. And the trips are allocated to the same proxy will share the same destination representation. So this is achieved by adjoint the generative process. We first join a pi. It is a one-hot vector indicating which proxy the trip is allocated from a category distribution. Then conditioning the pi and the parameters m and s, we generate the destination coordinates. Then we also equip the key proxy with an embedding matrix, and then we use w pi as the representation of the destination x. So the complete graphical model is shown in these figures. We would like to highlight that there are 2 flaws from this pi. First, the flaw is that this pi should be able to explain the observation of destination coordinates. And the other flaw is from pi to ri plus 1. So it should be able to effectively guide the spatial transition of the trips. So the information generative process implies the following log likelihood function. So integrate the latent variable in pi and c in high-dimensional space is very expensive, and the traditional MC based method is slow to converge. So for this reason, to yield an efficient inference algorithm, we resort to variational auto-encode and derive the following evidence law bounds. We use two neural networks to approximate the pository distribution. And the overall framework is shown here. We use two neural networks, encode 1 and encode 2, to approximate the pository distribution of latent variables c and pi, and then conditioning on the samples of these latent variables, we try to generate the observation R and X using another two generative networks. Here's the experiment. We use two large-scale trajectory taxi dataset, Chengdu dataset and Harbin dataset with about 3 million trips for each dataset. Here is the statistics. Here is the GPS point, the heat map of the GPS point of Harbin and Chengdu. So we evaluate our proposed BFAST on two tasks. First is most likely route prediction. The other one is route recovery from sparse trajectories. For the first task, we compare it with DeepSTC. This is a simplified version of DeepST without considering the impact of real-time traffic. And IN, which we also removed the destination from the model. And the CSIN, which is a state-of-the-art route decision model. And the first-order Markov model, and weighted shortest path, which returns the shortest path between origin and destination. On a weighted neural networks, where the weight is calculated using the speed from the historical trajectories. On the second task, we compare our proposed method with STRS, which it comprises two modules, time inference module and spatial transition modules. We replace these spatial transition modules with our proposed method and compare the performance with the original one. The evaluation measurement, we use two measurements, recall and end accuracy. Here, R is the ground truth route, and R hat R is the inferred route. To give a fair comparison, we truncate R hat by only preserving the first n segments. So intuitively, these two measurements try to calculate the proportion of the correctly predict route links. So here's the overall performance of all methods on the 2D set. We can see that our proposed method outperform our baseline method on both 2D sets. To further study the performance, we evaluated different methods. The performance of different methods when we increase the travel distance from 1 to 3 kilometers to 14 kilometers. Not surprisingly, as the travel distance increases, the performance of all methods decreases. This is because the number of possible travel routes between an origin and destination pairs grow exponentially with the route length. But in our case, our proposed method outperforms baseline method on both of these two datasets. We also have a result on route recovery. It is included in appendix. Thanks for your attention.
All right, do we have the author in the room? Is any of the authors in the Zoom room now? Well, I did have a question, but since there is no presenter, I don't see any question in the chat or Slack though. But I had question myself. Well, I guess it is what it is. So the second paper, I think we can start uploading the second paper. And I can maybe give a quick introduction. So the second paper is active model selection for positive unlabeled time series classification. And the presenters is Shen Liang, I think is a PhD student at Fudan University. Please go ahead.
My topic today is active model selection for positive unlabeled time series classification. Beginning with the introduction part, what is positive unlabeled time series classification, or PUTSC? Basically, this is a type of binary classification task with a training set comprised of a positive unlabeled set PL and a large unlabeled set U. So in this work, we will focus on transductive PUTSC, which actually uses PL and U to label U. So our work is not about PUTSC itself, rather it's about model selection for PUTSC, which we want to select the best PUTSC model and their classification results from multiple candidates. So in this work, we are going to focus on selection of models that follow the self-training one nearest neighbor, or ST1N paradigm. So this paradigm is actually the most widely used PUTSC paradigm to date. It has two steps. The first step is an iterative one nearest neighbor process to rank U examples by the possibility of being positive. So basically, we start with a ranked set initiated with PL and unranked set initiated with U. We are going to iteratively move unranked examples to the ranked set. So basically, in each iteration, we will find the currently unranked example that is closest to the ranked set, and we will move it to the ranked set. So the next step is to use a stopping criterion to determine the number of positive examples in the dataset, and then complete the entire labeling process. So actually, we have a concrete example here. So we start with a single PL example. We will iteratively rank 1, 2, and so on. And this particular iteration, the stopping criterion tells us that everything inside this circle should be labeled positive, and everything outside should be considered negative. So actually, this paradigm has two customizable components. One is the one nearest neighbor distance measure. The other is the stopping criterion. So combining these two can actually lead to over 1,000 candidate models to choose from. So to conduct model selection, our first challenge is that it is very hard to do so with very limited labeled examples from only one class. The solution is to use active learning, or AL, to query more labels from the user. So the second challenge is that in AL, the number of queries is usually limited. So we need an evaluation strategy to estimate the performances of each candidate with a given set of query U examples. We also need a sampling strategy to determine the order we query U labels with a limited number of queries allowed. Here we exploit a phenomenon called label propagation, which will be explained later. We now look into our proposed method. So our method actually contains two parts. The automatic warm-up part obtains the candidate models and also determines the sampling order, while in the user interaction part, we actively query labels from the user and provide user feedback. So the highlights of this framework in the first place is that it allows the user to determine their own evaluation metric. If you like to use F1 score or maybe precision, it is your choice. Also, it is anytime, so each time a query is made, we immediately provide the user with the current best so far, so the user can stop accepting queries at any time. And also, this method is completely parameter free. So our framework actually has two main components. One is the evaluation strategy. The second is the sampling strategy. We will begin with the evaluation strategy. So here, our objective is to estimate the candidate model performances with currently queried labels. So as to the performance metric, it is specified by the user, but here we will use F1 score as an example. So the evaluation strategy actually fits the performance metric by directly using the formula of that metric. And this leads to the need for pseudo labels. Here we present three types of labels. Actual labels are actual ground truth labels of U examples. They can be only known through querying. And we've got predicted labels, which are U labels predicted by the candidate models. And we've got pseudo labels, which are surrogates to actual labels. So when we estimate F1 scores, we actually use these pseudo labels in place of the actual labels. So our evaluation strategy follows this algorithm. The first step is to remove duplicate models. You can check our paper for exactly what this means. And also we will use each candidate model as a base model to estimate the F1 score of each candidate, and then use the total F1 score as the selection criterion. Basically, for each base model, we will first initiate the pseudo labels with the predicted labels. And also, the next part is the most important part, where we attempt to make the pseudo labels as close to the actual labels as possible. So finally, we will calculate the estimated F1 scores using the pseudo labels. So to conduct the key pseudo label calibration process, we need the concept of ST1 propagation chain, or SPC. So basically, in the original paradigm, we had this hash map called NN. So suppose the next example to rank is X, or NNX actually is its current nearest neighbor in the ranked set. So for this particular ordered set, if any example in it is the nearest neighbor of its subsequent example, and also this chain can no longer be extended, we call it an SPC. So here in this figure, we have actually 4 SPCs shown. So with SPC, we actually have an observation called ST1 label propagation, or SLP. So for any example xj on SPC, if it's actually negative, then intuitively all its subsequent examples, which we call xj primes on the SPC, may be actually negative. However, if xj is actually positive, then intuitively only some of its subsequent examples may actually be positive. So the rationale here is that the later an example appears on an SPC, the later it is ranked by ST1N, and the more likely it is negative. So to use this observation to guide pseudo-label calibration, we enforce the following principles. And now, due to time limitations, I will not go through them in detail. Basically, they try to fully utilize this observation while keeping our method perimeter-free and taking into consideration some of the weaknesses of existing PUTSC methods. So our focus here is how to efficiently implement these principles. We actually use a data structure called ST tree. So this is an ST tree in which each parent node is the nearest neighbor of its child. So we derive a concept called influence from ST tree. Given two examples as x and y, we say y is influenced by x if the node of y is a descendant of that of x, and also y has the same predicted label as x under the current base model. So the total number of U examples influenced by X is called its influence. So to implement the PLCPs for a queried example X, we use its queried actual label as the pseudo labels of all unqueried examples that are influenced by it. So the entire pseudo-label calibration process is shown here. Basically, for the current queried example next, for all of the examples influenced by it, if these examples have been queried before, then we will use their queried actual labels as their pseudo-labels. Otherwise, we will use the queried label of next as its pseudo-label. So I'm therefore completing the calibration process. So we embed the calibration process back into the original evaluation strategy, then we have the complete process of model evaluation. So this algorithm can actually be made incremental, which actually has a linear time complexity when we process each round of user interaction. Also, if you want to use other performance metrics than F1 score, you can simply change this line to whichever formula you desire. So that concludes our evaluation strategy, and we will move on to sampling strategies. So for the sampling strategy, what we want to do is to assign a score to each U example X, so we can query the examples with higher scores first. Here we want to maximize the effectiveness of the evaluation strategy by querying as few labels as possible. Now, since the evaluation strategy is influence-based, intuitively we want the sampling strategy to be influence-based too. So our first sampling strategy, called inf, uses the total influence of X under each model as its score. Sometimes it may not be enough if we only consider influence. Therefore, we will fuse influence with some traditional sampling strategies. The first traditional strategy we consider is disagreement sampling, where we fuse influence with maximum KL divergence. The second one is uncertainty sampling, where we fuse our influence method with classification uncertainty. Therefore, we have altogether 3 sampling strategies to pair with our evaluation strategy. So now we have our 2 strategies and we have our entire methods. We now look into the experimental results. As to experimental settings, here we use 2 types of datasets. The first one is the classic UCR datasets. We will actually use its latest version. The second one is the MIT BIH arrhythmia database, on which we will carry out a case study on ECG classification. As to candidate models, we have over 1,000 candidates to choose from. So here, please note that we are not proposing a PUTSC method in our paper. So these candidate models are not baseline methods. They are just candidates for our methods to choose from. So as to performances on the UCR datasets, the first question we want to answer is which combinations of the 2 strategies are the best? So for each strategy, we have some baseline methods and also our methods. So we will compare them in the following experiments. So as to the results, as you can see, we can actually identify 3 methods as our recommended methods for different percentages of U examples that are queried. So these 3 methods actually all use our evaluation strategy, but they use different sampling strategies. The first one uses a random sampling strategy, while the latter 2 use our influence-based sampling strategies. Now we compare our 3 recommended methods with some non-AL based baselines. The first is the optimal case, which is impossible in reality. Also, we have the case with no explicit model selection. We also consider the possibility of ensemble, which is basically the ensemble of multiple candidates via simple majority voting. And as to the choice of ensemble members, we follow this paper and provide 5 options. So as to the results, first we noticed that explicit model selection actually significantly outperforms no select, which performs pretty poorly. And also, as to our recommended methods, they significantly outperform their ensemble-based counterparts. So our recommendation here is that please use AL whenever it is possible. If not, use the best practicable alternative, which is DTW ensemble. So we now move on to the efficiency aspect, where we examine our user interaction response time, since we are proposing an AL-based method. So this time is defined as the time between the user labeling a queried U example and the next query being submitted to the user. What we want to show is that the recommended methods are efficient enough for real-world user interactions. First, we notice that the average response times are pretty tiny, while the maximum ones are actually reasonably short. Also, there is a huge difference between the 2, which actually indicates that most response times are actually pretty short. The longer ones are usually just outliers. So all in all, our recommended methods are fast enough for online user interaction. So we now present a case study in ECG classification, where we use our methods to detect a particular type of heart anomaly called VEV. So the data are 2 records from this database, and these are the results. First, we notice that, again, no explicit model selection performs very poorly, and our methods can achieve near optimal results by querying very few labels. Also, the best possible ensemble method performs well on this particular record, but it fails to do so on this one. As to efficiency, again, our methods have a very short response times, which are more than enough for online user interaction. So in conclusion, we have studied the problem of PUTSC model selection, focusing on ST1NN. We have drawn on active learning and utilized the label propagation phenomenon. We have proposed the concept of influence, and we have proposed an evaluation strategy and 3 sampling strategies. So for future work, we will attempt to robustify the evaluation strategy for cases with very few queried labels. We would also like to study inductive PUTSC model selection, and we would like to support more PUTSC paradigms. We would also like to use active learning to enhance the selected models. So that is all for my presentation. Thank you very much.
All right, thank you. So I think the author is actually here, Shen Liang, I see in the participant list. I haven't received any questions. Any questions, you can actually unmute yourself and ask the question directly. We have a little bit of time. All right. I think there is no question.
Let me maybe ask a question. So
yes.
This is Bernard. So I did not understand to which extent the fact that your data are time series came in here. So was this not just more generally work about generating labels, also work about active learning?
Okay, thanks for the question. Yes, this method is theoretically not limited to time series data. However, coming from a time series mining perspective, in the first place, the self-training one nearest neighbor method is particularly popular in the time series mining community. So basically, also our method, all of our baseline methods, including the candidate models, come from the time series mining community. So from an empirical perspective, this is mainly focused on time series data.
Thanks.
Thank you.
All right. So I guess while Yonjin, you upload the video, I just do a quick introduction of the third paper. The title is Neighbor Profile, Bagging Nearest Neighbors for Unsupervised Time Series Mining. And the presenter is Yondao He from Peking University.
Hello, my name is Yondao He, and I'm from Peking University. I'm so glad to present this work. Neighbor Profile. It is a simple but effective method to mine frequent and rare subsequences in the time series data. I will talk about the background of frequent pattern mining and norm detection in time series and existing work. Then I will introduce my method and the experiments. Time series is, well, intuitive, a sequence of real-valued scalars, as you can see, and its subsequence is a continuous shape, start from I to I plus m minus 1, and m is the subsequence length. It usually depends on the particular tasks. We assume it is given. And this is an example. It's an ECG signal. As you can see here, we can see a lot of repeated normal heartbeat and a single abnormal heartbeat. So we expect to mine frequent pattern like this because it is frequently occurring subsequences. And we want to mine anomaly like this because it's unusual and rare. And there have been a lot of work. And the most widely adopted one is the Motif and Discord. Motif is considered the frequent subsequence. It is defined as the one with the smallest first nearest neighbor distance. And Discord, on the contrary, is considered the unusual subsequence. It has the largest first nearest neighbor distance. Still consider this example. For each subsequence, we can calculate its first nearest neighbor distance. Well, let's say this subsequence we can calculate its first nearest neighbor distance, and we get this. And finally, we can get another series. It's the first nearest neighbor distance. Someone call it matrix profile, but to be exact, it is actually the first nearest neighbor distance for each of the subsequents in the original time series. And for the frequent pattern, you can see its distance is correspond to a very low value. And for the abnormal one, it usually has a large value here. So in this case, Motif and Discord can correctly identify the frequent and rare subsequences. Let's consider another case. Still an ECG signal, but it has extra 5 seconds here. So it contains another abnormal heartbeat. And in this case, we still can get the first nearest neighbor distance. And you can see there are a lot of high peaks. The 2 abnormal, it corresponds to here. But you can see even higher distances like this. So in this case, the highest, largest first nearest distance it corresponds to this subsequence. Actually, you can see it is not an abnormal or unusual subsequence. You can see a similar subsequence here, here, or here, here. So it is even frequent. This problem is called the twin freak problem. It's like that when the rare subsequences, though it is rare, but it can still occur more than once, like twice or 3 times. In this case, the Discord will fail to identify them. So why? We need to go back to talk about the instance of Motif and Discord. Let's recall the generic expression for density estimation. X is a subsequence, and the top is the probability, and the bottom is the volume. So this is a basic density estimation formula. And then there are 2 ways to further get the final estimate. One is Poisson window method or kernel density estimation. In this method, we fix V and counting K, counting how many sample instances falling in the neighborhood, falling in the volume, in the sphere. And this is quite famous. And there is the other method, K nearest neighbor. In this method, we fix K. For example, we let it equals 1 or 2 or 3, and then calculating the volume V. This is not so famous, and it is rarely used because it's not robust. Let's see some examples. The first is we use first nearest neighbor for the 1-dimensional case. Here we have a single instance. Given this instance, we want to estimate the density in the 1-dimensional space, and we can get the red curve. As you can see here, we have a very high peak when too close to the X prime, and this is even discontinuous. Another case is given a lot of normally distributed instances, still 1-dimensional case, and the right curve is the normal distribution, and the blue curve is the estimated one. As you can see, it is rather bizarre and has a lot of spikes. It is not robust. So Motif and Discord actually is the first nearest neighbor based density estimators. So they are not robust and can easily fail to identify the wanted subsequence. So someone may say, why not use K nearest neighbor? But how to choose K is not a trivial problem, because you have no idea how many anomalies in the time series data. And also, maintaining K nearest neighbor is time and space consuming. The method. Because first nearest neighbor is not robust, so naturally we consider using bagging to reduce the estimation variance and improve the robustness. Also, by sampling, we can reduce computational cost significantly. And this is the estimator given a sample. We want to estimate the density of a subsequence S, and it is proportional to this formula. And D is the nearest neighbor distance of S to the sample. And then we use the geometric mean to aggregate the results to avoid the numerical instability. And finally, we can get this form. We remove the constant term and take the opposite number. And if a high value will indicate a rare subsequences and a low value indicate a frequent one. But this is not the whole story. There's a problem. What if the subsequence S to be estimated also fall in the sample? In this case, the D, the nearest neighbor distance, will equal 0 and will cause numerical overflow. So we consider to increase it to adjust the nearest neighbor distance. We adjust the distance to its nearest neighbor in the sample. As you can see this figure, we increase the nearest neighbor distance D to the R nearest neighbor. So we use D tilde. And D tilde can also help stabilize the estimation, because you can view it as when you becomes too close to the instance, you have a very unstable and a very high peak here. But if it is bounded outside, you can have a rather stable estimation. So we increase the nearest neighbor distance. And finally, the neighbor profile looks like this. We use D tilde here. Let's see the example. Well, this is the previous result, the first nearest neighbor distance on matrix profile. And this is the result we get neighbor profile. As you can see, it is quite regular. And the highest value here corresponds to the subsequence, the two rare subsequence, and here, and here, they all correspond to the regular normal bit. And to calculate this, we use 100 samples. Each sample contains only 3 subsequences, and the total subsequences is over 5,000. So you can see how many computational resources can be saved. We also conduct qualitative and quantitative experiments. We just show the results that we can man the frequent subsequences and also the rare subsequences. And it was mentioning that neighbor profile can locate subsequences of interest, but maybe not all of them. So you need an extra similar subsequence searching procedure to find all the similar subsequences. But it's efficient, as you can see. And we use MIT BIH database and to check whether the man subsequence are the ground truth, and using AUC to evaluate the mining performance. And in the rare subsequence mining case and the frequent subsequence mining case, we win more cases than the first nearest neighbor distance. And conclusion, neighbor profile is, as you can see, is quite simple but effective. It can model the subsequence density robustly, and its advantages are simple, efficient, and robust. And also, they can allow different distance measures, and it can be easily tuned indirectly because it's efficient. Another thing is that it can painlessly inherit almost all the extensions based on Motif and Discord, like mining subsequences from multi-dimensional time series or include domain knowledge. And it cannot model local anomaly or frequent subsequences. That's all about my work. Thanks for watching. If you have any questions, please contact me. Thank you very much. Bye.
All right. I don't think the author is here. Is the author or any of the co-authors here? Yeah, unfortunately, we don't have the author or the co-authors here, so I don't think we can ask any questions. So with that, let's just move on to the fourth paper. The fourth paper is massively parallel change detection for satellite time series data with missing values. The presenter is Fabian Gieske. Fabian is an assistant professor at the Department of Computer Science of the University of Copenhagen, and he's actually here, so hopefully he would stay. So if you have questions after the presentation, you can ask him. Okay, let's start.
This work is about detecting changes in satellite time series data with missing values. In particular, we propose an efficient, massively parallel implementation for a well-known change detection method, which is called BFAST-Monitor. My name is Fabian Giesecke, and this is a joint work with Sabine Roska, Troels Henriksen, Jan Verbesselt, and Cosmin Wansha. Within the past few years, the amount of available satellite data has increased dramatically. For instance, the Sentinel program operated by the ESA has yielded more than 10 petabytes of data within the last 5 years. Modern satellites collect so-called multispectral image data over time. In the case of the Sentinel-2 mission, for instance, up to 13 grayscale images are obtained for each scene every 5 days. The RGB image that you can see here shows an area in the west of Denmark and is composed of such multispectral grayscale images. Satellite time series data often form the basis for change or break detection analysis. The sequence of images given on this slide, for instance, shows the impact of deforestation happening from 1996 to 2018 in an area in Peru. The availability of such high quality satellite data provides a huge opportunity to detect and monitor environmental changes at global scales, which is, among other things, crucial in the context of climate change. A common preprocessing step for various change detection tasks, such as deforestation analysis, is the extraction of wetness-related spectral vegetation indices per pixel, such as the so-called Normalized Difference Moisture Index, or NDMI for short. Such indices are used to extract information about the amount of vegetation per pixel. Roughly speaking, it tells us how green the area is that corresponds to a pixel at hand. For change detection analysis, sequences with hundreds of such images are considered, and this yields for each individual pixel a time series of reflectance measurements. This slide shows induced time series for 2 pixels, where the y-axis corresponds to the NDMI index and the x-axis to the date. One important change detection method in the field of remote sensing is the BFAST-Monitor approach, which is sketched here. More specifically, for each time series, a model is derived based on data given for a so-called history period, which is highlighted in green here. And in case the predictions generated by this model are not in line with the data available for the so-called monitoring period, which is highlighted in blue here, a break is detected. These breaks are illustrated as red dashed lines here on the slide. Note that except for specifying the history and the monitoring periods, no labels are needed. That is, the approach works in an unsupervised fashion. Furthermore, it's important to note that the individual time series give rise to different learning tasks. That is, the time series usually vary with respect to the number and the location of data points. This is, for instance, visible in the area highlighted by the yellow rectangle, where we have some data points for the first time series, but no data points for the second time series. The differences between the time series stem from the fact that clouds or other artifacts can include certain parts of an image for a given date, as it can be seen here again in the sequence of the 4 images introduced in the previous slide. This leads to missing values for the individual time series for certain dates, which usually vary from pixel to pixel. By applying this method to all pixels of a given scenario, one can obtain insights about where and when changes have happened in the observed area. In this case, here in the left image, we see the detected breaks for another area in Peru, where deforestation happened due to palm oil plantations. The right image shows the corresponding RGB image at the end of the monitoring phase. While BFAST-Monitor depicts a very powerful and robust change detection method, its application has so far required immense computational resources. That is, even processing medium-sized scenarios with a few million pixels using the commonly used implementation can easily take hours or even days on powerful compute servers. And this computational bottleneck has so far rendered global analysis infeasible in practice. The algorithm shown on this slide computes the desired breaks for the time series associated with a single pixel. Here, y corresponds to the target values and x to the features, which are extracted from the timestamps associated with the satellite images. From a computational perspective, BFAST-Monitor computes and applies a simple linear regression model for each individual pixel. Here, the first 4 steps of the algorithm compute this regression model, whereas steps 5 to 13 compare the predictions made by the model with the values given for the monitoring phase. Again, it is worth stressing that each time series generally gives rise to a different target vector y bar and a different data matrix x bar, which stem from removing the missing values in step 1. This renders the parallelization much more difficult since one is given many small subproblems of varying sizes. The main contribution of this work is a parallel implementation for BFAST-Monitor. The corresponding higher level specification is shown on the right-hand side of the slide and describes all available parallelism by means of data parallel constructs such as map, reduce, parallel prefix sums, and so on. The specification exhibits several levels of nested parallelism. For instance, the pixels can be treated completely independently from each other. Hence, the outer loop, which is represented here as a map, can be easily parallelized. However, the inner levels of parallelism induced by the other map, filter, reduce, and scan operations are much more difficult to exploit. The first 2 items here on the left-hand side sketch 2 extreme parallelization strategies. The first one is to simply utilize only the outermost level of parallelism by processing each pixel by 1 thread, and by efficiently sequentializing the inner parallelism. This strategy has the advantage that it performs the minimal amount of work, and it also enables aggressive fusion of sequential loops, which reduces the number of accesses to global memory, for instance. The first disadvantage is that the work across threads is unbalanced, which results in significant thread divergent overheads. And the second disadvantage is that the working set per thread is quite large, which makes it unlikely that caches are reused. The second extreme strategy is to fully flatten all levels of parallelism. The advantages are that the computations are balanced and that the transformed code respects the work and depth complexity of the original nested parallel program. The disadvantage, however, is that the transformation introduces instructional overhead in the form of many prefix sum computations, and that it destroys the temporal locality of the nested parallel program. Our approach could be seen as a midpoint between these 2 strategies, in the sense that we pad the inner parallel operations to have the same length. The regular sizes then allow various techniques to optimize the locality of reference. For example, inner parallel operations of the same size can be grouped and fused together to generate one CUDA kernel, which holds intermediate array, results in fast scratch pad memory, and which thus reduces the number of accesses to global memory. The next 2 slides present 2 illustrative examples of such optimizations. The first example addresses a batch matrix multiplication-like kernel, which is provided on the right-hand side here. As you can see, each array index is invariant to 2 of the 3 loops. For instance, A of J1, Q is invariant to the indices I and J2. This allows to tile the outermost loop, which is moved innermost and sequentialized, as well as the other 2 loops. The resulting outer loops basically form the CUDA grid, while the corresponding tiles form the CUDA block. So this optimization yields valuable speedups at kernel level, since each access to global memory is amortized by R reuses from register memory. You can see here on the right-hand side an evaluation of the performance gains in this figure, where D1 to D6 are synthetic data sets. As you can see, the register tiling approach outperforms its direct competitors by a factor of 2 to 3. The second optimization example addresses the case of batch matrix inverse. Here we exploit the fact that the time series generally have a length of less than 1024, which allows to group inner parallel operations of the same size into one CUDA kernel, and to keep the intermediate results in fast memory. Again, the performance gains of this optimization are shown in the figure at the bottom right here. As you can see, the optimized version outperforms its competitor by a factor of 5 to 6. The next slide here provides a comparison of the application level performance of the different methods. The table at the top summarizes again the properties of the different benchmark data sets used for the evaluation. The first competitor here, which is shown on the left-hand side, depicts a version in which matrix multiplication-like computations have been efficiently tiled, but which sequentializes the inner parallelism in all remaining computations. The second competitor implements a naive strategy that fuses everything into one kernel and that only exploits the outer parallelism. Finally, the third competitor is a C plus OpenMP parallel code version, which produces a parallel speedup of about 21 versus a sequential execution when run on a 16-core machine with two-way multi-threading, which is close to optimal. The overall benchmark comparison is provided here again in the figure at the bottom right. It can be seen that our optimized implementation, denoted by hours, yields valuable speedups over its competitors and outperforms, for instance, the parallel C implementation by a factor of 24 to 48, which validates the usefulness of our approach. The overall implementation is provided as a publicly available Python package, which resorts to PyOpenCL to integrate the optimized kernels. In addition to the kernel execution time, some time is also spent on pre-processing the images. Further, large images are processed in chunks, and this chunking can also cause some overhead in practice. This is also illustrated on the next slide. So our implementation allows to deal with very large scenarios given limited compute resources. For instance, this per large data set could be processed in about 17 seconds using a relatively old GPU compared to 25 hours, which were needed by the existing and commonly used ARM implementation on a machine with 6 CPU cores. At the top right corner, you can also see the runtimes needed for the different phases, including the pre-processing time, the time needed for the transfer between host and device, the kernel execution time, and the overhead caused by chunking. As you can see, the kernel execution time dominates, which allows to hide the overhead for the other phases by interleaving the computations. Finally, this example shows the output of our BFAST GPU implementation for an area covering the entire continental tropical Africa. Processing this massive scenario with more than 6 billion pixels took less than 90 hours using a single GPU, whereas it would take many years actually using the existing ARM implementation, even given powerful multi-core workstations. Thus, this example clearly demonstrates the usefulness and the potential of the implementation for future change detection analysis in remote sensing. To sum up, our work addresses the computational bottlenecks of the BFAST-Monitor approach, which is one of the state-of-the-art break detection methods in the field of remote sensing. We provide a high-level parallel specification along with several performance-critical kernel optimizations, and the new implementation allows to handle, for the first time, massive scenarios covering large parts of our Earth using little computational resources. The code is publicly available under the address shown here on the slide, and we very much hope that our implementation will facilitate large-scale change detection analysis in the future. Thank you very much for your attention.
All right. So we have the author here, Fabian is here. So if anybody has any questions, I don't see any questions in the Slack or chat. So if you have a question, you can just unmute and ask the question.
Oh, I have a quick question. I'm not sure what's the change detection results. Maybe it's as you show the images, and different colors shows how the changes were made over the years. So it's the color in the results shows the change detection. What's the result of change detection? Thank you.
Fabian, I think we have a problem in the audio. Everybody else understand the audio?
No, it's actually, it sounds very fun.
Yes. It's
Okay,
very
is it just from
very
Fabian's
squeaky
side
voice.
or just, yeah, maybe Fabian, do you want to mute and unmute yourself? I unfortunately still not understandable. Maybe you turn off your video and try again with just audio.
Or you can just respond to chat.
No, the audio is still bad. Maybe just turn the video off or maybe type in the chat.
Yeah, try to turn off the video.
Yeah, unfortunately it's the same. So maybe just a quick text on the chat. The same, basically the monitoring period is changed, hence we have different years and these results are plotted. Okay, I actually had a question, but given the technical difficulty, maybe I skip it. All right, so let me mute everybody. I still hear the, okay, now I think it's better. So let's move on with our last presentation. This is Skyline cohesive group queries in large road social networks. I think the presenter is Xian Li from Wuhan University. I think I saw the author in the list here. Yes, so hopefully you can also ask questions after the presentation.
Hello, everyone. My name is Qian Li. I am an undergraduate student from Wuhan University. I feel honored to be here to present our work, Skyline Cohesive Group Queries in Large Road Social Networks. This is joint work with Professor Yuanyuan Zhu from Wuhan University and Professor Jeffrey Xu Yu from the Chinese University of Hong Kong. With the rising popularity of GPS-enabled mobile devices, users can easily access to location-based services, which are services that utilize geographic data to provide services or information to users. The most common location-based services are traffic services, such as querying the nearest supermarket or navigating on Google Maps, and ride-sharing services on Uber. Offline games, social applications are also important location-based services, and representative businesses are Pokemon Go and Foursquare. Besides, location-based advertising, social events recommendation, trajectory analysis, place recommendation, and many other applications also add color to our daily life. The demand for location-based service boosts the emergence of location-based social networks, which can bridge the gap between the physical world and the virtual world of social networks. Let's look at an example of a road social network. The left figure is a social network where vertices are users and edges indicate relationships. The right figure is a road network where vertices are road junctions or ends. Solid circles are points of interest. Edges are road segments, and weights are the lengths of roads. Users' locations give the correspondence between social network and road network. In this example, users and locations are mapped by their subscripts. In other words, the location of VI in social network is RI in road network. We aim to find cohesive groups to enable group-based real-world activities and events. For example, a meeting organizer may need to choose a place to hold a meeting and decide whom to invite. A basketball player who wants to have an impromptu 3 versus 3 game may need to find a nearby court and players he can play with. A player of a live AR game, such as Pokemon Go, needs to check where and with whom she can play the game. In all these examples, the selected group members need to have a good social relationship to create a pleasant atmosphere in the activity and have small distances to a meeting point to save travel time. Therefore, the group should be cohesive in both social and road networks. But how can we evaluate social and spatial cohesiveness simultaneously? First, let's see how we define social and spatial cohesiveness. For spatial cohesiveness, we expect that the total travel cost of the group to be small, and all users' distances should be smaller than a threshold so that there are no outliers. For social cohesiveness, we expect that users have strong connections. In our work, we use K-core as the social cohesiveness metric. A K-core is a connected subgraph such that the minimum degree of vertices is no less than K. The core number of a subgraph is the minimum degree of all vertices. From the example below, we can get an intuition about K-core. From the inner gray oval out, the subgraphs are 4 core, 3 core, 2 core, and 1 core respectively. Now let's consider an example cohesive group query. Suppose that Alice is the user V1 at the location R1, and she wants to play an AR game of 5 people in one of the 4 nearby clubs at O1, O2, O3, and O4. The distances between the selected club and all 5 people should be less than 7. Each player should be familiar with at least 2 others, which means that the core number should be larger than 2. We aim to find cohesive road social groups under these constraints. In other words, we want to figure out who should she go with and where should she go. There are 3 good candidate groups for her to choose from. In the first group, the attendees are V1, V2, V3, V4, and V5. The meeting point is O1. The core number is 4 and the total distance is 24.9. In the second group, the attendees are V1, V2, V3, V4, and V6. The meeting point is O1. The core number is 3 and the total distance is 20.2. In the third group, the attendees are V1, V2, V4, V5, V7, and V8. The meeting point is O3. The core number is 2 and the total distance is 13. We can see that all 3 groups are good candidates, so that a flexible query should return none of them. But can existing work solve this problem? Well, most existing studies mainly aim at finding the maximum or minimum groups under certain social and spatial cohesiveness constraints. Work 5 finds the closest group for a given core number. Work 6 provides a heuristic method to select the group with the highest core number. Both of them lack the flexibility to balance the social cohesiveness and spatial cohesiveness. Work 7 tried to define a combined function to combine social, spatial cohesiveness, and group size, but their balancing parameters are hard to be specified. Therefore, existing work cannot find cohesive road social groups flexibly. Utilizing the concept of Skyline, we can define which groups are better than other groups and flexibly find all best groups. We can see that a group C1 dominates or is better than another group C2 if C1's core number is larger than C2's and C1's total distance is no larger than C2's. Or C1's core number equals to C2's and C1's total distance is smaller than C2's. The table below is an example of some groups. We can see that according to the definition of dominate, C4 dominates C1, C2, and C3. C6 dominates C5 and C8 dominates C7. So C4, C6, and C8 are called Skyline road social groups because they are not dominated by any other groups. If we solve the Skyline problem, we can find the best road social groups flexibly. In other words, a Skyline group query can find all three groups in the previous examples. As for the solutions, we would like to introduce the brute force algorithm first. Suppose that UQ is the querying user, C is the group size, R is the distance threshold, and K is the minimum core number. First, we can get candidate users and meeting point based on distances and K core. Then we select C-1 users randomly from the K core to see whether they can form a K core with C users. However, this is not efficient, as it has to enumerate an exponential number of KC cores. In fact, finding KC cores is an NP-complete problem. So how can we find KC cores more efficiently? We can borrow the power of NPlex. An NPlex is a connected subgraph edge such that the degree of any vertex in this subgraph is larger than VH minus N. The graph below has 4 vertices and the minimum degree is 2, so it is a 2-plex. Similarly, the next 3 graphs are 3-plex, 1-plex, and 3-plex respectively. Next, we build a connection between core and plex based on their definitions. We can see that the left graph is a 2-core of 4 vertices, and it is also a 2-plex. The next graph is the 2-core of 5 vertices, and it is also a 3-plex. The next 2 graphs follow the same law. In fact, we can prove that a K-core with C vertices, also called a KC core, is also a C-K plex. Note that KC core and C-K plex is not always the same. C-K plex is a KC core if and only if it has exactly C vertices. We explored many structural properties of C-K plex. Based on these properties, we can develop an algorithm much stronger than the brute force algorithm. The key idea is to transform the problem of finding Skyline cohesive groups to finding C-K plexes. The major difference is that here we use the branch and bound search of C-K plexes, and we can use those structural properties as powerful pruning strategies. It turns out that the efficient exact algorithm is significantly faster than the brute force algorithm. Another key observation is that we do not have to check all groups and maintain a set of Skyline groups. Instead, we only have to find the closest group for each possible core number K, and the resulting groups are sure to be Skyline groups. So we can greedily select the closest users. As we only find the best group for each K, there are even more techniques to speed up the search compared to the efficient exact algorithm. Although always adding the closest user at each step may lead to suboptimal groups, the additional distance compared to the best groups is small. To further speed up the algorithm, we designed an index called core distance tree or CD tree. The CD tree is used for storing the structure and distance information. When a specific query comes, we can get K-cores and distances from the CD tree. For a meeting point, to build a CD tree, we get users near the meeting point, like in the left figure. Then we get the induced subgraph of these users from the social network, like in the middle figure. Next, we build the tree structure index based on onion-like core structure and distances. We have conducted extensive experiments on 3 sets of real road social networks. First, we would like to show you a case study on the Foursquare social network and New York road network. 3 Skyline groups returned are presented in this figure. In each subfigure, the querying user is marked by a red pin. Other users are marked by blue pins, and the meeting point is marked by a purple star. We can see that from left to right, as K increases, the travel cost also increases. This validates the Skyline property of social and spatial cohesiveness and shows that Skyline cohesive group query can return a set of Skyline road social groups for users to choose, which can successfully balance the social cohesiveness and spatial cohesiveness. Now let's see the efficiency and the effect of our algorithms. The upper figure illustrates the result of the brute force algorithm, exact algorithm, and greedy algorithm on two datasets. We can see that the greedy algorithm significantly outperforms the exact algorithm, while the exact algorithm is also faster than the baseline brute force algorithm. Besides, we can also see that the greedy algorithm is robust to the change of parameters, but the exact algorithm and brute force algorithm is sensitive to the change of parameters. For the table below, we only have to focus on these bold numbers, which indicate the additional distances compared to the best groups. We can see that greedy algorithms only yield small additional distances, which is less than 5%. We also compared our greedy algorithm with CGNN, the state-of-the-art algorithm of group queries in road social networks. We slightly changed our setting to fit the problem of CGNN, as CGNN is a special case of our Skyline cohesive group query. We can see that our greedy algorithm can also solve the problem in CGNN, and our algorithm can find groups with higher core numbers and smaller total distances, which means that our groups are both socially and spatially more cohesive. Our algorithm is also faster than CGNN. To sum up, there are three main contributions in our work. We proposed a new Skyline cohesive group query model, which considers both social and spatial cohesiveness flexibly. We built the connection between core and plex and explored the structural properties, which are used as powerful pruning techniques to find those Skyline cohesive road social groups. We also designed a greedy algorithm and the CD tree index, which makes the Skyline cohesive group query much more efficient and effective. Thank you for listening to our presentation. Please feel free to contact us through these emails.
All right, so we have Chian here. Any questions? I haven't seen anything on Slack or the chat, but if anybody has questions, they can just unmute. So I have actually one question. So the cohesiveness I'm trying to understand for the spatial part, I understand this is the summation of the distances for various folks who are attending. What was that for social?
As for the social cohesiveness, we require the induced graph of these users to be a K-core, and a K-core is a subgraph that with a constraint of minimum degree. In other words, in this group, each user should be familiar with at least K other users.
I see. So that's basically the number of other users that can go to the same event. And this is just one degree separate from the user, or can it be like 2 degrees separate from the user? Or
this is different from what you said. I mean, in this induced subgraph, each user should be familiar with at least K users. I mean, the degree of a user should be larger than K. The minimum degree of the users should be larger than K.
So when you say familiar, you mean that it's one hop separate from the user in the social graph, or?
That is one hop, yeah.
Okay, so K people who are one hop away from the user.
Yes.
I see.
So I still have a question. So I found the problem mathematically, formally very interesting, very nice. And I have a question, however, about this say, social aspects if you want to apply that. So I can see two situations. Either people have the data, make the data available, then you configure a good group, and then still you have to ask the people and see whether they agree to actually join the group that, for instance, goes off for a play. Or the other way around, so you could so directly ask people whether they would be interested in joining this endeavor. And so then you run your algorithm, and so then you may have to tell some people that they are not wanted. So how would one use this technique?
Thank you for the question. And I suppose that you mean some users may be not available, right?
Either or, yes, or they may not be available, right? Or the other way around, if they are available, then you have to tell them, sorry, I have not chosen you.
If it is in that case, I think that you can, for example, if we find, if we ask about say 10 users and 5 of them replied that they can go with you, and you can use all these 5 users again as the querying users to query another groups.
Okay, that's nice. Yeah. Okay, thank you.
All right. So I think that's conclude our session today for research session 7. Thank you everybody for attending, especially the authors for being here and trying to answer the questions. We are a couple of minutes early, but other than that, everything I think went pretty smooth. Thank you, everyone. Bye.
Thank you. Thank you, Cyrus, and thanks everybody.
Thank you.
For staying up to the end, and see you tomorrow.
Bye.
See you. Bye.
Goodbye.
Bye.
Bye-bye.